There are actually 3 arc length formulas that we're going to learn, but today's is dealing with the rectangular coordinate system, and then later on we'll learn about a polar arc length and parametric arc length. On YouTube, Black Pen Red Pen has a really cool proof for the formula for arc length using that good old Pythagorean theorem. So I'll link that here so that you can check it out if you want to know how this formula came to be. To find arc length, we need the derivative of our function and an interval. We have our interval, let's find the derivative. Arc length is sometimes referred to as S. 0 to 2, our interval. Go ahead and plug that into your calculator, and you get 20.633. Sometimes arc length questions ask for the perimeter of a shaded region. Notice this area between the 2 curves. If they ask you for the perimeter, then you would use the arc length of the blue curve from A to B and add it to the arc length of the purple curve from A to B to get the perimeter of the shaded region. A slope field is a graphical representation of a set of slopes obtained from a differential equation. Remember that a differential equation involves a derivative. That derivative represents the slopes for a function. Even if you cannot separate variables and integrate, you can still use a differential equation to plot the slopes for a function. Example 1. Find the slopes given by the differential equation dy over dx is equal to negative x over y at the following points. dy over dx is our slope, so to find the slope at a particular point, we take negative x and divide it by y. Now continue evaluating the slopes at each of these points. Why can't you find slopes when y equals 0? That's because y is in our denominator and you can't divide by 0. For example 2, we're going to fill out the slope field for all the remaining dots here on the graph at right. Okay, so you can see these tiny little lines at each particular point represent slopes. Fill in the slopes at all the points that do not have their slopes filled in. Anytime x is 0, our slope will be 0. A slope of 0 is a horizontal line. The slope at 1, 2 would be negative 1 over 2. The slope at 1, 3 would be negative 1 over 3. The slope at 2, 2 is 1. The slope at 2, 2 is negative 1. The slope at 3, 3 will also be negative 1. The slope at 2, negative 1 is going to be positive 2. At 2, negative 2, it's going to be positive 1. At 3, negative 3, it's going to be positive 1. Go ahead and fill in the rest of the slopes yourself. We couldn't find the slopes at 0 because they were undefined, but undefined slopes are vertical lines. So at each of our x values, we can include a vertical slope line. In example 2, you made what is known as a slope field. Starting at the point 0, 1, follow the flow of the slopes to sketch the solution curve containing 0, 1. Your graph should be parallel to the slope lines and be like an average of the slopes whenever it goes between the lines. Your curve also must represent a function whose domain is the largest possible open interval containing the given point. At 0, 1, we have a horizontal slope. As we move toward the positive x-axis, we'll be sloping downward until our slope becomes completely vertical. Going to the left, slope downward, but positive slopes this time. Now, I could keep going. It looks like this is a circle, but I need this curve to be a function with the largest possible domain. That's why I chose from negative radius to positive radius, and that's why we have this semicircle. At negative 1, 1, we have a negative slope. As you go toward the x-axis, it becomes steeper until it's vertical. As you go away, it becomes less steep until it's horizontal, and it is symmetrical on the other side. This would be our lower semicircle in order for it to still be a function. If it's a semicircle and our radius is 3, then I can kind of follow the idea of a semicircle for our solution curve. The most common student error in sketching a particular solution to a differential equation is to extend the sketch too far and create a graph which is not a function. So watch out for that. Make sure all your particular solution graphs pass the vertical line test. For example 4, we're going to solve the differential equation that we just made a slope field for in the previous examples. We're doing that by separation of variables, beginning by multiplying both sides by y times dx. We do that to separate our variables. Y is on one side, x is on the other. Now we can integrate. Remember that 2c is the same as c, and that is why c is unchanged. Just to not have that negative in front. Solving for y yields two solutions, the positive square root c minus x squared or the negative square root c minus x squared. We write it separately so that each solution is a function. Our positive semicircle takes care of any points that would be above the x-axis. Our negative semicircle would be the format of our particular solution that we would use if we're going through a point below the x-axis. Find the particular solution for this differential equation whose graph passes through the point 0, 1. All right, so 0, 1 is above the x-axis, so we're going to use the positive version of our semicircle equation. Our point is 0, 1, so I'll plug in 1 for y and 0 for x to solve for c, making c equal to 1. The particular solution for this one would be positive root 1 minus x squared. For the particular solution that passes through 0, negative 3, we use the negative semicircle equation because that point is below the x-axis. Plug in negative 3 for y and 0 for x. In this case, c is equal to 9. So y is equal to negative root 9 minus x squared. For the differential equation y prime equals 1 over y, draw the slope field in the dot coordinate plane at the right, graph the particular solutions passing through the points negative 2, negative 1, and 2, 2 as functions of x, solve the differential equation, and then write as functions the particular solutions for the differential equation whose graph passes through negative 2, negative 1, and 2, 2. The slope field shouldn't be too difficult. It is simply 1 divided by whatever your y value is. So on the x-axis, we'll have 1 divided by 0, which is undefined slopes, which is vertical lines. When y is positive 1, all our slopes will be 1. When y is positive 2, all our slopes will be 1/2. When y is positive 3, will be 1/3, and then you'll have some symmetry below the x-axis with negative slopes. Fill it in. Negative 2, negative 1 is this point right here. I'm not going to be able to cross over the x-axis because you can see your slopes will go back to the right and I will fail the vertical line test. So I'll go up to the x-axis, which is a vertical slope. This slope gets less and less steep. For 2, 2, again, I will not be able to cross the x-axis, so we'll go down to it, which is a vertical. And then going up from here, the slope gets less and less steep. To solve our differential equation, I'm going to exchange y prime for our notation dy over dx. Multiply both sides by y dx. Integrate once you've separated your variables. Remember that a square root is an operator, so you cannot remove the c from under the square root. As a function, negative 2, negative 1 is our negative version. It looks like a square root graph, a sideways parabola. And we'll plug in negative 1 for y and -2 for x to solve for c. Making c equal to 5. We will plug in 2 into our positive version. And in this case, c is equal to 0.